Hi, my name is Muhammad Ifanati bin Karazab and my method number is 1232117. So let's continue to my friend.
Hi, my name is Muhammad bin Zadi and my metric number is 1233293. Let's go to our next member.
Hello, my name is Adam Haziq. My metric number is 1232109. I'm the final member of this group. So let's move to our lab.
So what is the objective of this experiment? So first of all is to describe the kinematic model of the differential graph mobile robot DDMR. Second one is to explain the difference between open loop and closed loop control system in mobile robot application. The third one is to implement a proportional controller in MATLAB simulating for mobile robot motion control. The fourth one is to evaluate the effect of controller gains on the performance of the robot, including stability and response characteristics. And last but not least is to analyze the tracking error and system response of the mobile robots under different conditions. So what is the description of the robot parameters? The robot used in this lab is the Pioneer 3DX, which is a differential graph mobile robot. The robot motion is described using three parameters. The first of all is X coordinate. X coordinate is representing the robot's horizontal positions, and the second one is Y coordinate is to representing the robot vertical position. And for the pi is representing the robot orientation angles. The robot is controlled using the controller U and also controller W. For the controller U, which is for the linear velocity, and the controller W is used for the angular velocity. By controlling these two inputs, the robot can move to a desired position and orientation. So for our lab, we use MATLAB Simulink. Why we use MATLAB Simulink? MATLAB Simulink allows us to simulate a robot movement without requiring a robot, without requiring a physical robot. So it has a few advantages that make us to use it as for our lab. First of all, it's easy to design control system. It also fast simulation and testing, and it easy visualization of robots movement and output graph. And it also has a few disadvantages by using this MATLAB simulation. First of all, is the simulation may not perfectly represent real-world conditions. So the sensor, noise, and physical disturbance are not fully represented in the either model. So there's a few advantages and disadvantages of MATLAB simulation. That's all.
Okay. So hi guys, so this is our lab 2 setup as per usual. So as you can see here, first thing first, the lab given is to download the MATLAB simulink file from this link. So we need to open this link, and then we appear like this, download, and we need to download, and then we open the MATLAB. Okay, we open the MATLAB, and then we need to open the new file, which is distance back the lab 2 open loop, and then we open, and then we open here, and then it will appear like this. So for the lab 2 also, for the next part, which is closed loop, we need to open here also, and then we need to, you can see here, based on the table given, so it already gives us x equals to y equals to 0, and we need to find how much input can make x equal to 2. So first thing first, we open this and we put 0.4, and then we will get, we then run like always, open the output, and then we get that the desired position for x is 2. Okay, here 2. Okay. After that, we continue to the next part, which is we try to put the initial condition 0.8, and then we want to see the how much x will give in the output. So we run back, and then we open the output, and then we get the output, which is 4, 4. And then we continue to the last part. So we use to try to put the initial value, which is 1.5. Okay, 1.5, and then we run back as always, open the output, and then the output given is 6. So here, what is this? 4, 6, like that. Okay, so guys, we continue to the part B, which is closed loop control. So here is the block diagram. So we already rearranged and we already connect all the stations. So we follow the table 2, which is for the desired position, x is 2 and y is 0. So we need to change for the KPU and KPW value by according to our table. So before that, we need to change here. PKPU for proportional is 0.5, and then for the PKPW also 0.5. So we run, and we need to check the output. So here the output for the part 1, we can see here the output become like this. So we continue to the next part. So we change for the proportional is 1, and then for this also 1 as table given. So we run, and we will see it's already increased, as you guys can see here, already increased. So we continue to the next part. We try to follow the table, graph for proportional, and for this also 12, and then like this. Okay, here like this. So this is the output for the able to. So we continue to the next part. We need to change the S value equal to -5. We tried to use -5, and for Y we tried to use 5. So here what this is. So we continue to put here 0.5, and then for PID also, for this also 0.5, and then let's look what we have. We open the output, and yeah, the output already give like this. So we continue to the next part. We change for the controller parameter. For the proportional we change to 1, and then for the KPW we change also to 1. So we run back, and then we open the output given like this. So you can see the change between 0.5 and 1. So let's move on to 12. So we put 12 here, and then we put 12 here, and then we run and then we open the output, and the output given like this. So here what is this? So we continue to the next part, which is part C, to see and observe the closed control loop with the preset of steady state error. So from this part we can improve the steady state error performance by following the part B. So by using the same desired position as before. So I used to x equals to 2 constant value, and y equals to 0. Then for controller U, we change back to 1 for proportional, and then for controller W we change for 1 also for their proportional. So the value will be like this. Here what it is. We continue to the next part, which is we change back -5, and then we change this also 5, and then we change for the proportional 1, and we need to change their integral to get the perfect graph. So we change their to 0.005, and for the derivative we change to -0.001. So we will see. So for the control W will remain as before. So we run back, and then we open the output, and the output will be like this.
So basically, for part A, we have conduct an open loop control experiment on the mobile robot. The robot was required to move along the x-axis with y equal to 0. We tested 3 desired positions, which were 2, 4, and also 6 by varying the input velocity. So basically, from the result here, we observed that the larger target distance required higher input values, and the robot moved according to the predefined input and reached the destination faster when higher velocity was applied. However, since open loop control has no feedback mechanism, the robot could not correct any movement, error or disturbance. So in conclusion, open loop control is simple to implement, but its accuracy depends heavily on the chosen input value. For part B, we have implemented a closed loop control system using proportional controllers in Simulink. So we have test to target position, which is 20 and -55, while varying the controller gains from 0.5, 1, and 12. So basically, from our observation here, we can see that lower gains result in slower but smoother movement. However, for moderate gains, improve the response speeds and reduce settling time. Meanwhile, for very high gains, cause faster movement but introducing overshoot and oscillation before stabilizing. As you can see here in the graph, the difference between each graph that we vary the gains. So overall, closed loop control performed better than open loop control because the robot continuously corrected its motion using the feedback loop. So let's go for part C. For part C, we have investigated the effect of steady state error in the closed loop systems and improved the controller performance using PID tuning. We observed that when using proportional control alone, cause a small remaining error between the actual and desired position. So by introducing integral and derivative terms, the robot achieved more accurate positioning and smoother movement, as you can see here in the graph. So basically, as the conclusion, controller tuning is important because proportional gain improves response speeds and integral gain reduce steady state error, and derivative gains help reduce oscillation for a more stable system. So let's move to the questions for discussions. Basically, for question 1, varying the desired position in open loop control affects the required input and traveling time of the robot. So what I want to say is larger distance require higher input velocity to reach the target faster. However, because there is no feedback system, the robot cannot correct any movement error, making open loop control less accurate for precise positioning. Okay, so for question 2, controller parameters greatly influence the robot output. Lower proportional gains produce slower but smoother movement, while higher gains improve response speeds but may cause overshoot and oscillation. Therefore, suitable controller tuning is important to balance the speed, accuracy, and also the stability of the system. Right now, let's move to question 3. For question 3, steady state error occurs because proportional control alone may not completely eliminate the difference between the desired and also actual position. Other factors such as modeling inaccuracies and system limitations may also contribute to the error, causing the robot to stop slightly away from the actual target. Okay, now let's move to the last question. For question 4, controller parameters significantly affect the system performance. The proportional gain improves response speeds, and the integral gain helps to reduce the steady state error, and the derivative gain reduces the oscillation for smoother motion. Proper PID tuning allows the robot to move accurately and stably.